in the context of the exponential model, we talked about how the geometric model really was a prelude to the discrete version of where we would where we're headed with the exponential model over in the continuous world. So let's go back real quick to this notion of the standard geometric PMF, probability mass function, because I'm going to go back to a little bit of that view of what are we doing and why, which is all about modeling, trying to come up and with some way to predict the future. And we talked a little bit in previous lessons about how we can take this generalized form of the geometric PMF, some constant a times some constant b raised to the x power, and x was a integer that started with 0 and could then become positive. And under our normalizing condition about the sum of all the probabilities had to be equal to 1, we found out that b was equal to 1 minus a, and that if we wanted to shift the model, because we were only interested in values above a certain range, then we would get a b x minus x naught being that base value. Right? We're going to follow the same kind of process really as we introduce in the continuous world this notion of a standard exponential function that is going to allow us to take time or space into the continuous realm and relax some of the restrictions that we have in our discrete part. And so there'll be a couple of things here that might seem like they come out of nowhere until we get into a specific application. Let's let beta be equal to the natural log of 1 over b. So sort of that same kind of b that we had before, right? And that's going to tell us that beta is going to have to be greater than 0 since b is less than 1. Right? We know that back up in here. This is the same kind of a and b thing, right? And from this, then, we know that e to the beta is equal to 1 over b, or that b, the constant, is equal to e to the minus beta. So if I only knew beta, well then I would know b. And sometimes in practice what we do is we assume a value for beta and it follows through then what some of these other constants are. Notice also that b to the x then is equal to e to the minus beta x. And that gives us then a new distribution function for x that's going to be equal to a new constant a prime times b, which is, or b to the x that is, which is this guy here, and so that's e to the minus beta x, and x is greater than or equal to 0. If we're interested in space, well then we use x. If we're interested in time, we'll substitute in a different variable here, usually t, to emphasize that we're looking at time. And in a graphical sense, then, our function, when we plot it out, is at 0 going to be equal to a prime, and then it'll be just a nice exponential decay on out. And there's our fx of x. Right? So we're still left with, okay, that's a nice generic form, but what the heck do we do with it? So let's go and look at a slightly different normalizing condition than what we had used before. And in this case, what we'll do is go directly to the standard property of a density function, that we're going to integrate our density function over its entire range, and it has to be equal to unity. And in this case, since x is a non-negative number, it'll go from 0 to positive infinity. And now we just substitute in, we get a prime e to the minus beta x has to equal 1. And so now we just process this on through, right? So we take the antiderivative, we get minus a prime over beta e to the minus beta x, and evaluate that from 0 to infinity, and we'll get 0 minus, then a minus a prime over beta, right? Because e to the minus infinity is going to give us here our 0 number, and then put in our 0 for x, and we get a 1 minus a prime over beta. And then once again set that equal to 1, and therefore we find out a nice little result that a prime is equal to beta. And that's good news, because now that means that our function is equal to beta e to the minus beta x. It's a single parameter function. That's always good, although it does leave us with the question of, well, how do we find beta? Right? One last thing before we go over and address that question, and that is that if we have a shift that we're interested in, it's like we talked about before, for those earthquake magnitudes, we looked at magnitudes, say, greater than 3.75, and so then our shift will just simply be that up here in the argument where we have x, we'll shift things over. So in general, that would be our x naught, and you can substitute in your x naught there. Note then that we have a new restriction on our x value, that it has to be greater than our shift value, which in this example was our magnitude.